Welcome back to another video. Dr. Tarsia Hubert here, and in this video we're going to talk about more inverse trigonometric functions. In the last video we talked about the inverse sine and cosine functions, and so today in this video we're going to look at all of the other functions, including the tangent, inverse tangent, secant, cosecant, and cotangent functions. Alrighty, so starting off we want to look at the tangent function. So I have y equal tangent x here in the chart for the tangent function. And if we remember what the tangent function looked like, the domain of the tangent function was all x except x was undefined at every odd multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. At each of those, you have an asymptote, which is just a dashed line going down, which means your graph doesn't touch that point, but it gets really close to it, okay? And then your range was negative infinity to infinity. So whenever we get ready to do the inverse tangent, so I'm going to write inverse tangent over here, y equal inverse tangent of x. We want to switch the domain and range, but we end up having to fix our range, just like with the sine and the cosine, we end up having a restricted range. And so I don't know if I did a great job of saying why we have to restrict the range in the last video, but one of the most important things is that in order for it to be a function, remember each x has to map to only one y. So we can't have an x mapping to multiple y. So we have to pick a specific period of the graph to where we won't start repeating y's, okay? And so in this tangent function, if we look at the original tangent function, this is what it looked like. The period that we pick, so when I say we don't start repeating, you just pick a part of the graph where it's not doing the same thing. Once you start to do the same thing, that's where you have to cut it out. So if we were to keep going after pi over 2, we will start repeating that path. So we pick just this portion of the graph, okay? We don't have any multiple y's. This is a function on this part of the graph. So you want to pick a part of the graph where it is a function. Each x maps to only one y, or it passes the vertical line test, okay? So now if we look at the domain in this portion of the graph, it's negative pi over 2 to pi over 2, where the negative pi over 2 and the pi over 2 is not included. So that portion will become the range of our inverse function, okay? And so basically what we do is we switch all of our x's and our y's. And so if I switch if I switch the x and y for the first one, it will be undefined. So I'm just going to switch the x and y's for the ones where we don't have an undefined. So we will have negative 1, negative pi over 4. We will have 0, 0, and we will have 1 pi over 4. So now where it was undefined before at negative pi over 2 and pi over 2, where we had asymptotes, we'll still have asymptotes on our inverse function. They'll just go in a different direction. So we have vertical asymptotes here. So when we switch it, we'll have horizontal asymptotes. So let's graph that. So we have negative pi over 4 and pi over 4. So let's make this pi over 4. Let's make this negative pi over 4. So at negative 1, if we go back at negative 1, we're at negative pi over 4. So we'll be here. At 0, we're at 0. And at 1, we'll be at pi over 4. And let's make this pi over 2. And this negative pi over 2. And so now we will have horizontal asymptotes at pi over 2 and negative pi over 2. All right, this is the inverse tangent function. And our graph would actually, because look at our domain. Our domain don't just stop there. So if it would have just stopped there, it would have just been, a graph between here, which kind of looks like inverse sine, right? But our domain is actually negative infinity to infinity. So that means we have points for every x and for every x. So that means our graph continues here. Oh, my computer's doing that tripping thing. But it will continue there and it will continue in this direction. And so this is what your inverse trigonometric function looks like. So it almost is like, or your inverse tangent. So if you see the tangent function, which is here in the middle, it looks like it's just rotated around and flipped over. So it looks similar, it's just rotated and flipped over. And so what we notice about this for this inverse tangent function is that it is increasing. If we were walking on it, we're going up. So it's increasing on its domain from negative infinity to infinity, and it is continuous on its domain, meaning we could draw it without picking up our pen or pencil. The x and y intercept is 0, 0. This one is symmetric to the origin, so inverse tangent will be an odd function. And then we also have horizontal asymptotes at pi over 2 and negative pi over 2. And so here's a more formal graph. This mine is a sketch. I know it's not perfect, but here's a more perfect graph. And you can see it here. So this is your inverse tangent, also called the arctangent. So here is the formal definition. And basically what y is the angle that will give you the tangent value of that x, whatever your x is. And so our range is restricted between negative pi over 2 and pi over 2 for the inverse tangent. And so we also have inverse cotangent, inverse secant, and inverse cosecant. And basically they have the same range. Well, the inverse cotangent has a range from 0 to pi. The inverse cosecant has a range from negative pi over 2 to pi over 2. And then the inverse secant has a range from 0 to pi, except for the fact that it can't be pi over 2. Okay, and so these are just the inverse cotangent, inverse secant, and inverse cosecant summed up. And I also have a chart here that has all of the inverse functions with their domain and their range. Okay, the range is broken down into the interval, but also the quadrant. So this is going to be important when you're solving equations that involve using the inverse. That you have to know it, because if you put a value in a calculator, it only gives you one answer, but there's always going to be two different answers because of the two different quadrants that it could be in. Okay, so let's look at some examples of how to use the inverse tangent, and I think we'll use one of these other ones as well. So we want to find the degree measure. So this one specifically says find the angle in degrees. We want to find the degree measure for the following. And the first one is arctangent of 1 equal theta. So basically we're looking for, if I rewrite that for part A, if I rewrite that, this is the same as saying tangent of theta equal 1. We want to know, where does the tangent of theta equal 1? Okay. Well, remember, tangent is sine over cosine. So that means, where is the sine and cosine the same? If you go back to your unit circle, sine and cosine is the same at 45 degrees. So in this case, theta is equal to 45 degrees. Alrighty. Tangent is also 1 in the third quadrant. Now, in the third quadrant, that would be 100. That'll be 225. 180 plus 45. That'll be 225 degrees. But that is not within our range of negative pi over 2 to pi over 2, which is negative 90 degrees to 90 degrees. It doesn't fit within that range, so that will be our only answer. And then if I rewrite this secant, inverse secant one, it'll be the same as secant theta equal to 2. So we want to know, where is the secant of theta 2? And so remember, secant is 1 over cosine. So if you think about it, that is going to be where our cosine is 1/2. Because 1 over 1/2 is equal to 2. So I'm just thinking about that. So 1 over cosine will have to be 1/2 in order for us to get 2, because we would do the keep, change, flip. You will multiply by that reciprocal of the denominator, which is 2. So where is cosine 1/2? Cosine is 1/2 at 60 degrees. Okay, so your cosine is 1/2 at 60 degrees. So this would be theta is equal to 60 degrees. Alrighty, cosine is also 1/2 in the fourth quadrant, which would be 360 minus 60, which is 300 degrees. But remember, for secant, if we go back to secant, our range is 0 to pi over 2 and pi over 2 to pi. So from 0 to 90 degrees and 90 to 180 degrees. And in this case, so I said the other one was 300 degrees, so that one doesn't fall in the range. So your only solution here would be 60 degrees. Okay, so now we want to look at some examples that require you to use the calculator. So we want to find y in radians if y is equal to inverse cosecant of -3, and also arc cotangent of -0.3541. Now, we know we will have to use a calculator on these because we don't know from our special angles where the cosecant is -3, and we definitely don't know from our special angles where the cotangent is negative 0.3541. So I'm going to show you how to plug these in the calculator, okay? Okay, so I'm using Desmos.com. This time I'm at /scientific. This brings me to a scientific calculator, and I'm originally on main. On main, I want to make sure that I have it in the right measurement. So in this case, I wanted to find theta in degrees. So I'll leave my calculator in degrees. No, radians. I'm sorry. I wanted to find it in radians, so I'm going to put this in radians. And then I'm also going to go here to where it says function. This is going to give me more functions. And as you can see, I have my inverse functions here. And for our first example, we wanted to find the inverse cosecant of -3. Notice we don't have cosecant, secant, and tangent functions, so we have to use their reciprocal. So since cosecant is the reciprocal of sine, we will use inverse sine. But instead of putting the inverse sine of -3, we will put the inverse sine of -1/3. We would take the reciprocal of the -3. So we will put 1 over -3. I'll go out of my fraction and close the parentheses and hit enter, and you can see that the inverse cosecant of -3 would be -0.33983,69095. This would be my answer right here, okay? Also, for part B, it says to find theta in degrees. So now I'm going to change this back to degrees. Well, no, it says radians. I'm sorry. I'm going to keep it in radians. If it wanted you to put in degrees, you can change the mode here. All right, I'm going to go back to function. This time it's the arc cotangent. So I'm going to use inverse tangent because that's the reciprocal. And instead of me putting negative 0.3541, I'm going to put 1 over negative 0.3541. I'm going to go out of that fraction and close my parentheses. And I get negative 1.23047. Now this is an angle, a negative angle. It's a negative angle, and we have to think about what is the range of tangent. So the range of tangent is from negative pi over 2 to pi over 2. And just so you know what pi over 2 is, we'll do pi over 2 here. Pi over 2 is 1.57. So the range is between negative 1.57 and 1.57. So I needed to jump back over here to show you all what I'm trying to get to. So the range of inverse tangent is in quadrants 1 and 4. So these two quadrants, 1 and 4. Negative 1.23, which is what we got, would be, if negative pi over 2 is here, then negative 1.23 is going to be over here somewhere. So this would be our angle theta, which is negative 1.23. Now, the only thing we have to consider is that the range of tangent and the range of cotangent is different. The range of cotangent is in quadrants 1 and 2, so from 0 to pi. So that means we need to find where else the cotangent would have that same value, which is going to be over here in the second quadrant, because cotangent is negative. Tangent and cotangent are negative in quadrants 4 and 2. So to find that same reference angle, we will use this as our reference angle of 1.23. We would have to do 180 or pi, because this is pi minus that answer. So we would do pi minus 1.23, and that's to find the angle with the same reference, okay? So if you do pi plus that answer or pi minus that answer, however you write it, because that was a negative 1.23, so really you're doing pi plus that, you get theta to be 1.911 and some more ones in radians, okay? So this is the radian measure of theta for part B, okay? So whenever you're doing inverse cotangent, cosecant, and secant, you just have to make sure that the ranges are the same. And we didn't have that issue with cosecant because it shared the same range as sine, and so we were good there, all righty? Alrighty, we're going to look at one last example for this video, and we want to evaluate this without using the calculator. We want to take the sine of the inverse tangent of 3 over 2. Remember that the inverse function represents an angle. So this is basically saying we're taking the sine of the angle, but we want to figure out what is that angle that gives us a tangent of 3/2. Okay, and one way we can do that is we can set up a triangle. So if we go back to our very basics of when we first defined our trigonometric functions, we use right triangles. And imagine that's a nice right triangle. I know it's a little crazy, but if this is our angle, we'll call it theta. So we're going to let theta represent this. Then the angle theta that has a tangent of 3/2, because remember the inverse tangent of theta, or the inverse tangent of 3/2 is the same as saying the tangent of theta equal 3/2. So I'm looking for the angle theta that gives me a tangent of 3/2. Remember, tangent is opposite over adjacent, so that would be 3, and that would be 2. Our opposite side would be 3. Our adjacent side would be 2. So we would need to figure out what is our hypotenuse. Okay, so remember this is a right triangle. For our hypotenuse, we'll call it r, which we did before. R is equal to the square root of our x squared plus y squared. Yeah, remember that? So r is equal to the square root of x, which is the 2, our adjacent side plus our 3 squared, the y. So that's 4 plus 9, which is 13. So r is equal to the square root of 13. And so we have this side being the square root of 13. So we have defined our triangle. Now we will use that triangle to figure out what is the sine of theta. That's basically what we're looking at now. What is the sine of theta? And so sine is the opposite. So it'll be 3 over the hypotenuse, which is the square root of 13. We can't leave that square root of 13 in the denominator, so we have to rationalize the denominator by multiplying top and bottom by square root of 13. And so that becomes 3 square roots of 13 all over 13. And that's what the sine of that angle would be. 3 square roots of 13 all over 13. Alrighty, so that's how you would find the sine of inverse tangent of 3/2. You will create the triangle, label the angle, whatever you want to call it, theta, alpha, beta, y, whatever you want to call it, and create a triangle that gives you a tangent of 3/2. Once you create that triangle, then you find the sine of that angle. If you have any questions whatsoever about what I did here or anything that I did in this video, please don't hesitate to put them in the comments below. Hopefully everything made sense to you, and if you really liked it and you understood everything, go ahead and hit the like button for me. And if you haven't already, by now you should have already hit subscribe, but if not, go ahead and hit that subscribe button. Thank you all for watching, and I will see you in the next video.